Okay, let's continue with our functions of several variables. So in the first section of this chapter, we just talked about these functions of several variables and how to get a general understanding of them. So I would remind you, there are the syllabus of the course. There are 4 important chapters. There was chapter 11, chapter 12, chapter 13. There will be chapter 14 plus a little bit of chapter 15. So chapter 11 was mostly about linear algebra, about planes and lines and things like that. Chapter 12 was mostly about vector valued functions. And we had these 2 things for the first midterm. This chapter is mostly about functions of several variables, which is, well, I think the most important part of the book, which we would spend most of our time. Chapter 14 is about multiple integral, which is kind of this is the version of the integral which is suitable for these functions. Chapter 15 is something I might talk a little bit about, which is not in the book. It depends on if you are going to have time or not, which is just a very short mention of things called manifolds. We will see. Okay, so and chapter 13 is, well, that's the whole thing we need to know. So we had these 2 things for the midterm. We will have these 2 things for the final. Maybe a bonus question from the manifolds. The functions of several variables which we are talking about has a few different sections. First, just the domain, which we talked about. Then we should talk about the limits. Just like we talked about the limit of vector valued functions, we should talk about the limit of functions of several variables. However, it is different. You know, the limit of vector valued functions was very, very, very similar to vector of the single valued functions which we had seen before in Calc 1, Calc 2, Calc B or Calc C. But here the limit is really different. It's something else. Then we should talk about partial derivatives. And then derivative or differential in general. Differential has 2 important things about it. One is so-called the chain rule, which is it's not something easy. It's kind of very important thing. And another thing which I might talk about, it depends if we have time or not, is something called implicit function theorem, which is, it's the higher dimensional version of implicit function theorem. It depends if we have enough time to talk about it or not. And then finally, there are some applications of finding extrema of functions, maximums, minimums, and things like that. So finding extreme of the function. Also, it's related to another subject called Lagrange multipliers. And then in the last part, we have double integrals and triple integrals. And if we have extra time, I would tell you about so-called Stokes theorem. This would be related to this chapter 15, which is related to electromagnetism and things like that. This part would be more an application to both physics and economics. This part, Stokes theorem, is more related to physics. Anyway, so that's for kind of having a picture. No, the final is not cumulative. However, as you know, you can't really separate math, different parts of math, right? You should know the first part, but I'm not going to ask about the first two chapters, 11 and 12, directly. The explicit questions are going to be from chapter 13 and 14. Also, I didn't take the test on the integrals here. We skipped the integrals. And we skipped spherical and cylindrical coordinates. So the point is that, am I going to ask about them in the final or not? Well, the answer in some sense is yes, because, I mean, this chapter, all of it is about integrals. So it's a lot more advanced than the integrals we saw here. So it contains that. We are going to talk about integrals a lot. So one suggestion is that if you forgot integrals, it's a very good time. I would send you a PDF on the Blackboard, go and review integrals. So maybe that would be good if I kind of add some questions about integrals to your homework. So review integrals. Just one-dimensional integrals, which you have seen before. What about spherical and cylindrical coordinates? Yes, they also appear here. They are, we use them in taking integrals. So we should know spherical and cylindrical coordinates too. So these two things would also appear in the final exam. Okay. So is there any question about the first part of our class, 13.1? If no, let's continue with the limit of these functions. So functions of several variables, limit, and continuity. Okay. So let's remember, what does limit really mean, or continuity? They are very, very, very related things. So when we have a function, say f from R to R in the classical calculus, the things you probably have seen before, we could look at the graph of the function. And we would say it's continuous simply if it looks continuous. So this would be an example of a continuous function. And this would be an example of a discontinuous function. So this is continuous, and this is discontinuous function. Okay. So what is it really about? A function we say is continuous. If you look at the point in the domain, here domain is the x-axis. If you look at a point in domains, look at this red point, for example. If you look at the points which are close to that point, so let's say this point, this red point, let's call it A. Let's look at the points which are pretty close to this point A. So it would be, these are, say, the points which are close to this A, these blue points around A, okay? If I look at the value of the function for these points, so for any blue point here, for example, this green one is one of them, I can look at the value of the function at that green point. It would be something. We can look at the value of the function at that red point. It would be something else. These two numbers are close to each other. So the value of the function at A, f of A, and f of another point, say B, B is a close point to A, f of B, are close to each other if A and B are close to each other themselves. Okay, so if you have 2 points in the domain which they are close to each other, the value of the function at those 2 points are also close to each other. That's what we call a continuous function. Now here on the other function we have on the right hand side, I can take this point here to be A and very, very, very nearby point B. F of A is this red point. You see, there's a hole here. It means that is not where the function is defined. This is where the function is defined, the field point. Okay? This is F of A. B is very close to A, you see? But if I look at the value of F, F of B would be here, which is not close to A. So there is a jump. A and B are close to each other, but the value of the function at those 2 points are not. There's a jump between them. Okay, that's what we mean by continuous function in one-dimensional case. What is the key concept there? The key concept is when two things are close to each other. See, we talked about A and B being close to each other, or F of A and F of B being close or not being close to each other. So the point which matters is that if 2 points are close to each other or not. The abstract mathematical notion for that is something we call a neighborhood. The neighborhood. We say B is in a neighborhood of A, actually. So what does that mean? So for example, here, suppose we have a function, suppose we are in two-dimensional. Okay, suppose we have a function from R2 to R. Okay, so the domain is inside the two-dimensional plane. So the domain of this function F is inside the two-dimensional space. Suppose I have a point with value with coordinates X and Y inside the domain, right? Suppose that's the domain of the function. This is the domain of the function. In the one-dimensional functions, F, if it's a function from R to R, maybe it's better to show it with another letter. Let's say G is a function from R to R. If I take a point A here, the points which are close to A, they form an open interval. So points close to A, what do I mean by that? I mean an open interval around A. So for example, the length of the interval is epsilon. So this interval would start at A minus epsilon over 2. This point here would be A minus epsilon over 2, right? We would go back by half of the epsilon. And the other point here would be A plus epsilon over 2. From A, I would go forward by epsilon over 2. This interval is, this is the set of points if epsilon is a small. So if epsilon is a small number, this interval is, this is the set of points which are pretty close to A. We call it a small neighborhood of A. Okay, so if we have a function from R to R, a neighborhood of each point is a one-dimensional thing. So here the neighborhood is an interval. Interval is something one-dimensional. Now, if our function is from R2 to R, like the function F we have here, if I take any point A in the domain, so A is the point with coordinates X and Y, what is the set of points which are close to A? The set of points which are close to the A actually are these points. These are the points which are close to A, right? It's not one-dimensional anymore. It's something two-dimensional. So the set of points which are close to A here becomes something two-dimensional. So, and this is what we call here a neighborhood of A. So a neighborhood of A would be the set of points which are pretty close to A, which, as you can see, it's inside a circle around A. Actually, the correct word for that, when we are considering the inside of the circle, it's not circle, it's disk. We call it disk. And we call it actually open disk because we don't want to include the points on the boundary. It's not like that. We don't want to include the points on the boundary. We call it an open disk. It's two-dimensional version of an open interval. Okay, so this is actually the set of points. So if I want to write that more mathematically, if A is a point in R2 with coordinates X and Y, the set of points which are close to A, they form a disk with radius epsilon. So there are the points of the form, say, B, where the distance between A and B is less than epsilon. It exactly means these points inside this disk, inside this circle. Well, if say B has a coordinates B1, well, maybe it's better to change my notation slightly, I'm sorry. So for A, I would use A1 and A2 for the coordinates of A. So the point A, say, is equal to A1 and A2. And B is any other point inside this disk, which I showed with X and Y. So I would look at the points B equal to X and Y such that distance of A and B is less than epsilon. What is the distance between A and B? Well, we should subtract the first coordinates, square it, subtract the second coordinates, square it, and take the square root. It should be less than epsilon. Now I can square both sides. It means A1 minus X squared plus A2 minus Y squared should be less than epsilon squared. We know this exactly describes this inside this disk. This is called, we call this thing, when the radius is epsilon, we call this thing epsilon neighborhood of A. Okay, and as you can see, it's something two-dimensional. Now, what do I mean by a function f from R2 to R to be continuous at a point A? So suppose A equals A1, A2 is a point in the domain of the function. I say f is continuous at A if, okay, I just need to exactly repeat what I had in one-dimensional case. I say f is continuous at A if, let me say it informally, and then I would write down the formal definition, which is a little more challenging. It's one of the hard steps in the mathematics, actually, in 19th, maybe in 18th century. Informally, it means f of another point, B1, B2, would be close to f of A1, A2 if the point B with coordinates B1, B2 is close to point A equals A1, A2. So in other words, if we have a function from R2 to R, if I have 2 points A and B, if they are very close to each other, their distance is something like epsilon, the value of f of a and f of b should be also close to each other. If this holds, I would say f is continuous at a. If it doesn't hold, I would say f is not continuous at a. Okay, someone has asked to take a look at the previous slide. Well, I didn't say almost anything here. It's just, I just defined epsilon neighborhood of a to be the set of points where their distance with a is less than epsilon, which they form an open disk around a with radius epsilon. Okay. Okay, that's the informal definition. But there is a formal definition too. I wouldn't tell you the more mathematical definition. Let's see if we need that. Because it's not mentioned in the book, if it's really necessary, I would tell you of a more advanced definition of continuity and limits. But now knowing what is a continuous function helps us to define the limits of a function with, say, two variables. So if I have a function f of x and y, and say a point a equals a1, a2 in the domain, I say limits of the function f, where x and y, they go to a, which is a1, a2. I would say the limit is a number. Remember, the limit is a number here, is a number L if, so let's look at the domain here again. This is the point A. I would say the limit of the function f at this, around this point or at this point A is L if for any very, 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 very small epsilon, if for any small epsilon, which is a positive number, epsilon is a very small positive number, there exists another positive number, say delta, such that if our points, if the points I'm taking are, if such that if x is in delta neighborhood of x, delta neighborhood of a, which means if the x is a point, maybe I'm sorry again, x is not a good notation. Say a point B. If another point B is in delta neighborhood of A, which means their distance is less than delta, then f of B, the distance between f of B and L, the distance between f of B and L is less than epsilon. Okay, this might look a little confusing. I know this is the definition of limits. If you haven't seen this definition, it might be slightly confusing to you. So let me explain that a little more carefully. So we have a function f from here, we have from R2 to R, right? And I'm taking a point in the domain in R2. This is my point A in the domain in R2. Say this is the point here A, okay? I say the limit of the function f at this point A is equal to a number L. This is this number L. If what I'm going to say happens, what is that? If for any small epsilon that, for example, you give me 1 over 1,000, 1 over billion, 1 over 10 to the 10, doesn't matter how small you choose, very for any small epsilon, whenever epsilon is where it's positive, for any small epsilon you give me, I should be able to find another small number, I call it delta. I should be able to find that, such that if we look at the points in domain which their distance to A is less than delta, like this, which means they're pretty close to A, then the value of the function at those points should be closer to L, closer than epsilon. So their distance from L should be less than epsilon. That's the definition of limit for functions of several variables. So maybe let's look at an example. So in the midterm, I wanted you to just be able to compute the limit. I didn't want you to use the definition to write down the limit. But now I want you to use this mathematical definition to compute the limit. Delta just represents another positive number. Delta is the distance of the points in the domain. So let me write down one example. It might help you to grasp the idea better. So let me write down the definition again. So we have a function f of x and y. I would say the limit of f at the point x and y, which goes to a1, a2, is equal to L if for any positive epsilon, there exists a positive delta such that if the distance of points like B from epsilon is less than delta, I can guarantee that f of B is closer to L. The distance between f of B and L is less than epsilon. That's the definition of limits. Now let's see what it really means in one example. It might give us a better idea if we look at one explicit example. Let's say I have a function f of x and y equal to 5x squared y, x squared plus y squared over x squared plus y squared. Okay, this is an example of a function f from R2 to R. The domain has two variables, x and y. So the domain is two-dimensional. What is the domain of this function? What is the domain exactly? Well, I should see what are the restrictions on x and y. The only case which here the function is not defined is where the denominator is 0. So I don't want the denominator to be 0. It should not be equal to 0. What does it mean? When is it 0? What does it mean for x squared plus y squared to be 0? Well, there's just one case where x squared plus y squared would be 0. Note that x squared is a non-negative number, y squared is a non-negative number. If their sum is 0, both of them have to be 0. So yeah, so it only means both of them, x and y, both of them are equal to 0. So domain of this function is the whole R2 minus the origin. So if I want to sketch the domain of the function, it does not contain the origin, but it contains every other point in the plane. That would be the domain of the function, right? So f of 0 and 0 is not defined because f of 0 and 0 would be 5 times 0 times 0 over 0. So this is not defined. Okay. But on the other hand, although the value of the function is not defined, we can use this new concept, so-called limit of the function at that point, at 0 and 0. Before I do it, I want you to try this definition this formal logical definition to see what is the limit of this function at 0 and 0, okay? Try to do that. Try to use this definition to see what you would get. Try it for a few minutes to see if you would get the answer or not. Okay, does anyone have an answer? Maybe this function doesn't have a limit, or does it have a limit? So does anyone have any idea? Okay, let me give you one hint. You should use this logical definition to prove what is the limit. Usually first, you should try to guess what is the limit, and then use this definition to prove that. I would tell you the limit is 0. Try to use this definition to prove the fact that the limit of this function, although it is not defined at the origin, is 0. Okay, maybe it's better if I write it. So let me write down the definition of limit again one more time. I would say limit of the function f of x and y, where x and y goes to a point, say a1, a2, is equal to L if for every, I would read this like upside down A, I would read it for every positive epsilon, there exists, I would read this E, which is right to left, I would read it, there exists a positive delta. So maybe I should define these things. Maybe you haven't seen this thing before. It means for every, these are just notation. Rather than just writing for every, I use this notation. And then this other one means there exists. There exists a positive delta such that whenever the distance between 2 points, say A and B, where A is A1, A2, and B is, say, B1, B2, whenever their distance is less than delta, then the distance between the value of their functions would be less than epsilon. Now I have an explicit function, right? My function is 5x squared y over x squared plus y squared. I should say this is an example which you would definitely see in the exam. This is one of the most important concepts in this book. So now I want to prove not this example, something similar probably. I want to say the limit of this function when x and y goes to the point 0 and 0, I want to prove the limit is 0, right? So I should say for every positive epsilon you give me, I can find a positive delta such that for any point B, which is distance from this point 0 and 0 is less than delta, then the value of their, sorry, that's not f of a, there's a typo here. The limit is L if L minus f of b is less than epsilon, typo. Here should be L. So then L, this number minus f of b, which is b1 and b2, is less than epsilon. This is what I need to prove, okay? Okay, here L is 0, so rather than L, I can just write down 0, and the absolute value of 0 minus f of b1, b2 is just the absolute value of f of b1, b2. So what is f of b1, b2? I should write down what is f of b1, b2. It would be 5x squared. Here it would be b1 squared times y, here would be b2, over x squared. Here it's b1 squared plus y squared. Here it's b2 squared. I should show this thing can be made, I can make it smaller than epsilon. Okay? That's what I need to do. This is what I need to prove. But when can I make this thing small? I can make it small when the distance between 0 and 0 and b1 is less than delta. Well, the distance of b1 to 0, 0 is b1 squared plus b2 squared, the square root of that, right? If you have a point b1, b2, its distance from the origin by the Pythagorean theorem is b1 squared plus b2 squared, square root of that. This number should be less than delta. So I should say there exists a delta such that if b1 squared plus b2 squared, its square root is less than delta, then 5b1 squared b2 over b1 squared plus b2 squared would be less than epsilon. I think this is the first example of really a pure mathematical argument in this course. So what I really need to prove is that I should show I can find positive delta such that whenever b1 squared plus b2 squared, its square root is less than delta, then 5b1 squared b2 over b1 squared plus b2 squared would be less than epsilon. So the only point here is I should really find delta. What is delta? I should find this delta. I know it's confusing. It's, as I said, if you haven't seen this thing before, it takes a while. You should see a few examples. After a while, we will understand what it means. Okay, now let's look at this thing, 5b1 squared b2 over b1 squared plus b2 squared. This is this thing, 5b1 squared b2, its absolute value actually. b2 over b1 squared plus b2 squared. I want to say this thing should be less than epsilon. But this thing itself is equal to, say, 5b2 times b1 squared over b1 squared plus b2 squared. Okay, I just bring 5b2 outside of numerator. Look at this part, b1 squared over b1 squared plus b2 squared. What do I know about this fraction? What do I know about this fraction b1 squared over b1 squared plus b2 squared? What I know is that, look at denominator. Denominator has the b1 squared, which I have in numerator, but it also has another thing, another positive number. Yeah, that is correct. So in denominator, I have some more positive numbers. So denominator is greater than numerator. Therefore, the whole thing is less than 1, right? Whenever we have two positive numbers, whenever we are dividing two positive numbers, when the denominator is less than numerator, the whole fraction is less than 1. So this thing is less or equal than 5b2 squared, b2 times 1, which is just 5b2. Okay? Right? Okay. But on the other hand, 5b2 its absolute value, sorry, we have absolute value, we should not forget about that. The absolute value is equal to the square root of b2 squared. Do you agree? I can, rather than b2, the absolute value of b2, I can write down the square root of b2 squared. On the other hand, b2 squared is less than b1 squared plus b2 squared. Of course, it's less than that. Right? We are adding another positive number here, so we are making it larger. And we want this thing to be less than epsilon. So let me say it one more time. I want this thing to be less than epsilon, but this thing itself, after doing some basic algebra, I learned this thing itself is less than 5 times the square root of b1 squared plus b2 squared. So if this thing here is less than epsilon, so if this thing here is less than epsilon, that would imply 5b1 squared b2 over b1 squared plus b2 squared. Its absolute value would be less than epsilon 2, right? When I have a is less than b, if b is less than c, it means a is less than c. So here, what I have circled with green, if this thing is less than 5 square root of b1 squared plus b2 squared, if 5 square root of b1 squared plus b2 squared itself is less than epsilon, it would imply what I started with would be less than epsilon. But if I want this condition to hold, it means b1 squared plus b2 squared, its square root, should be less than epsilon over 5. And now I claim we have solved this problem. Why? Well, I wanted to say, if, look at up here, I wanted to say if b1 square root of b1 squared plus b2 squared is less than some delta, then 5, the absolute value of 5 b1 squared b2 over b1 squared plus b2 squared is less than the epsilon. I found my delta. What is that delta? That delta is what I have here. It is where b1 squared plus b2 squared, its absolute value should be less than that. So delta is actually epsilon over 5. And that's the answer to this question. So I know if you haven't seen this kind of argument before, it would be quite challenging for you actually. Even in the history of mathematics, it took a while for people to define this kind of very formal approach to limits, but it's quite important. So we would do more example of this thing. Don't worry. So let's do one more example. So it was an example of a case where a limit exists. Delta can be any positive number. So the question someone has asked, could delta be any number? Delta can be any positive number. But if there is any delta, then the limit exists. If I can't find any delta, if I can't find any positive delta, it means the limit does not exist. So we saw an example where limit really exists, which means we can find the delta. There are examples where the limit does not exist. So how can we show the limit does not exist? So suppose I have another function, f of x and y. It's a function of two variables, say x squared minus y squared over x squared plus y squared, the whole thing squared. Now the question is that, does this function have limits? The question is, does this function have limits at the origin, 0 and 0? If it does, what's the limit? If it doesn't, well, show me there is no limit. Okay. Actually, this function does not have limit. One way to see a function does, well, this is the most common way of showing a function does not have limit. This is another thing you would definitely see in the final exam. So this is the domain. Okay, there is a question. So to prove it, do we assume f of b minus L less than epsilon and then find delta? Yes, that is the strategy. We would assume f of b is closer to L, closer than epsilon. The distance between f of b and L is less than epsilon. And then we would try to find some delta which guarantee this condition would hold. But sometimes it is not possible, like this case. What is the domain of the function here? Well, the domain of this function is where this is defined. It's where x squared plus y squared is non-zero, which means x and y is not equal to 0 and 0. So the domain is everything minus this origin. So domain is the whole plane R2 minus this origin 0 and 0, right? That's the domain of this function. Now, although it's not defined there, one might hope that the function has limit there, although it is not defined. Okay. The answer is no, it doesn't. It does not have limit. How do we show that? Usually, the way to prove a function does not have limit somewhere is to approach that point from different directions. This is one direction I can approach this point 0 and 0. This is another direction I can approach 0 and 0, right? So as you can see, I'm taking two different directions. One might be able to approach this function, okay? So what does this green arrow represent? Well, these are the points of the form x and y, where y is actually 0, right? Here, y is 0. So what does it mean to approach the origin? It simply means x is going towards 0. Okay. What about the points on the other arrow, on the red arrow? Well, they are the points of the form x and y where x is 0 now, right? We are on the y-axis, x is 0. So what does it mean here to approach the origin? Well, it simply means y is going to 0. Okay. Now, that's the first step of showing a function does not have limit. What is the second step? The second step is to computing f of these two forms of function, two arrows, the points on these two arrows. So first we have f of, say, this green, this blue arrow, which are of the form x and 0. Y is 0 here, right? So it would be x squared minus 0 over x squared plus 0, the whole thing squared. But x squared minus 0 is x squared. If we squared, it would be x to the 4. X squared plus 0 is x squared. If we squared, it would be x to the 4. They cancel, they become 1. So the value of the function on this blue arrow is equal to 1, right? What is the value of the function on this red arrow? Well, f of 0 and y would be, well, here x is 0, so it would be 0 minus y squared over 0 plus y squared, the whole thing squared. Well, what is that? Minus y squared squared, well, the minus sign would go away, it would be y to the 4. It's divided by y over 4, it's also 1. Okay, so I failed. I was hoping if I go on two different directions towards the origin, I would get different values. The point is that if I can find different directions going towards the origin, if I get different value for the function on those directions, that would show the function does not have limits. I failed a little, but there is still something I can do. Maybe I should choose a better direction. What if I choose this direction? What is this direction? Well, this direction are the points x and y, which they are on the line y equals x. Well, if y is equal to x, the forms of the form x and y are actually x and x, because x and y are equal, and x is going to 0, right? What does it mean to go towards the origin? It means x is going to 0. What is the value of the function for these points? For the points like f of x and x? Well, it would be x squared minus y squared, but it's again x squared, over x squared plus y squared, but x and y are equal on that direction, so it would be again x squared. Well, x squared and x squared cancel. It would be 0 over x to the 4, which is 0. Oh, that's great. So on this blue line, the value is 0, whereas on this green line, the value of the function is 0, whereas on the green, on the red, and on the red line, the value of the function is 1. That means the function does not have limit here. Why? Because a function has limits if at a point, if when you are getting closer and closer to that point, the f of function would get closer and closer to one fixed value. But if you get closer and closer to the origin, on different directions, you would get different values. It means there is no fixed value anymore. It really depends on how you're approaching 0. It means there is no fixed limits, and therefore the function does not have a limit. So that proves the fact that the function x squared minus y squared over x squared plus y squared, the whole thing squared, does not have a limit at the origin. Okay. Okay, so when we have, okay, there is a question. Let me see. Is there another way to prove there is no limit? Yeah, there are many different ways. We would see some of them. Wouldn't the denominator be 2x squared? Oh, yeah, you're right. Was there a typo there? Yeah, it would be 2x squared, which would be 2 times x to the 4, which is 4x. Actually, it would be 4x squared, which is still 0. Okay, so let's go back. We had a function f of x and y. It was equal to 5x squared y over x squared plus y. So this function, as you can see, is not defined when x and y are equal to 0 and 0. It only makes sense if x and y are not equal to 0. But actually, if x and y are equal to 0, the limit of the function is 0. We computed that as well. You would see here, this was the proof that the limit of function at that point is 0. In that case, we say we can extend the function to the point which it wasn't originally defined. So the function, originally it was defined on R2 minus the origin, right? The domain was everywhere minus the origin. But now that it has limit at the origin, we can extend the function to the origin. So the function would be defined everywhere. Okay, now if it's defined everywhere, what would be the value of the function at the origin? I would define the value of the function at the origin would be to be 0. And the good thing is that the function we get at the end would be continuous. So whenever a function is not defined at a point, just like this function was not defined at the center, but it has a limit at that point, we can extend the function to that point which it wasn't originally defined to define the function, well here, define the function everywhere. And that point which we couldn't define the function, it was we call it singularity. But now that we can extend the function to that point, we call it removable singularity, which means it's the singularity we can remove. It's not a real singularity. But sometimes, like this other function, x squared minus y squared, this other function, x squared minus y squared over x squared plus y squared, the whole thing squared. Again, we have singularity at the origin. Again, we have singularity at the origin. But we can't remove it. So, because there is no limit there, we call that non-removable singularity. Now, this kind of singularity, first of all, is very similar to what people call a black hole. Like in the center of the black hole, they say we have singularity. They usually refer to the same thing, but the non-removable one. So let me show you one page of the book to understand what does a singularity mean a little bit better. Now, let's look at this example here. This is the function where this function here, you would see the graph of this function where it has singularity at the origin. So the function is not defined at the origin, okay? But as you can see, if you are really close to the origin, I'm not sure if it's really very visible here or not, but if you are very close to the origin, the graph of the function is also very close to 0. Do you see that? So it's not defined in the origin. There is a hole in the origin, but you can feel that hole. You can just put a point in that hole in the origin, and the function would be a continuous surface. The function would pass through the origin. It's an example of a removable singularity. Now this one is the second function we looked at, x squared minus y squared over x squared plus y squared squared. It's here. Actually, it's a non-removable singularity. It really doesn't get, maybe this graph is more understandable. This is another example of removable singularity. There is no way to feel this hole. This hole goes towards infinity, you know? It doesn't have any limit. It goes to infinity. Or this other one, it doesn't go to infinity, but the way it converges to 0 is that if you go towards 0 in different directions, you would get different values. So let me try to show, let me see if I can show you how this thing works. So let's see if we can plot the graph of this function to see this thing better. Because here what we have is kind of not 3D. Okay, let's look at this page. Okay, so what was our function? Our function z, for example, was equal to x squared minus y squared over x squared plus y squared, the whole thing to the power, the whole thing squared, right? So this is how this function looks like. Let's see if we can see that. Yeah. So the point is that if I want to fill this hole here, I should decide what value this function should have at the origin, right? But I mean, this graph is not very accurate, unfortunately. Let me see if I can make it look a little better. Yeah, this is a lot better. So if I walk through this path here, there is like a valley here where I show it with my mouse. This here, for example, say the elevation from sea level, let's say it's a mountain. If I go from here, the value of the function is 0 all the way to the origin. If I go on this wall here, the value of the function is 1 all the way through the origin. So what should be the correct value of this function at the center? Well, it simply doesn't make sense because it can't be, I mean, it should be both 1 and 0, because if I approach the center from here, I expect to get the value 0. But if I converge to the origin from this wall, I expect to get the value 1. You probably can see the value, the function goes down here. This wall goes down here, as you can see. Okay, it seems what I asked is a lot. So if you see the value of the function goes down here, it's not correct. That's because the software does not understand infinite. Actually, this wall should continue up to this z-axis, all the way to this z-axis. It doesn't go down at any point. So if you walk on this wall, you would get here. If you walk here, from here, you would get here. You have two different directions. These two different directions give you different. Yeah, I asked the number of grid lines to be, it was, in this picture, it's 100. I asked it to be 1,000, and apparently that's too much. So we need, we need a quantum computer. Let me try to do that for the other function. What was the other function? So it really doesn't work. The other function was, which doesn't have limit, is 1 over x squared plus y squared. This one also has singularity here. So if we, okay, that's not how it should look like. Maybe just, that was good apparently. Okay, so as you can see, this function goes to infinity at the origin, right? And there is no, well, maybe if I even make it smaller, you can see it better. There is no way to extend the function to that singular point, to this point at the origin. It goes to infinity. And you see, we didn't have any problem with sketching surfaces before, but now we would get to difficulties. The main reason is that here, we are dealing, as you can see, it doesn't show the grid. We are dealing with things which they are going to infinity. And usually, this, well, I mean, that's the point. These softwares, they don't really understand the infinity. Okay, so it was another example of a function which has so-called singularity at the origin. And it's non-removable singularity. There isn't anything we can do, right? But there is, and we saw another function which we can remove the singularity. Let's look at that one. So maybe I should refresh this page. Okay, so let's look at, it's interesting that my computer doesn't handle this thing because, well, I use my computer for gaming, so that's strange, but anyway. Let's look at, say, 5x squared y over x squared plus y squared. This is the function which I said we can extend it to the origin. This is the graph of this function. Now, as you can see, there is no problem of extending this. I mean, even this software has extended the function to the origin. You see, there's no hole there. It's a smooth, complete surface. There's nothing wrong with that. We can zoom in and go towards the origin. As you can see, there is nothing wrong with that. Maybe we can extend the grid lines. to see it better. But there is nothing wrong with this function at the origin. We can extend this function. So this function is not defined at 0, right? The denominator would be 0. But the denominator is 0 in the same way that, okay, so you can see here the function, there is no problem of extending the function to 0. So we call that a removable singularity. Okay, so what does this thing really mean? If you want to have a feeling, it's like if a function y is equal to 1 over x, the graph of the function looks like this. Actually, this function has singularity when x is 0, right? And there is no way to remove that. Look at the graph of the function. It goes to plus infinity on one direction of 0, goes to minus infinity at the other direction. So this is an example of non-removable singularity. But I give you another example. Consider y is equal to x over x. Okay, well, that's actually, you might say, well, I can cancel x with x and it would be equal to 1, right? But that argument is not really true. Why? Because when x is 0, you can't do that. When x is 0, you can't cancel x with x. And when x is 0, you would get 0 over 0, right? And it's not defined. So the graph of the function would be what I have here, but everywhere up to 0, there's a hole there. We can't define it there, not defined. So you might say it's not defined there and there is a singularity there. There's a singularity there. But this singularity is fake. You know, it's very artificial. There is no singularity there. You can just add that point and just ignore that singularity. I mean, this function is really 1. The way I present it by writing it as x over x, this artificial way gives us this singularity. So x over x is not defined at 0, but this is an example of removable singularity. We can write it in a better way and there wouldn't be a singularity anymore. I can just say y is actually just equal to 1. Forget this way of writing, and then we can feel the singularity point there, whereas we can't do that here. There's no way of doing that here. So we had that in 5x squared over y over x squared plus y squared. But here, x squared minus y squared over x squared plus y squared squared is an example of this phenomenon. I should say one more thing. If I have a function y equals x over x, the function would be, as I said, it would look like this. There would be a hole when x is 0, right? So if I ask you, this is say f of x. So if I ask you what is f of 0, the correct answer is not defined. There is no 0 over 0. But if I ask you what is the limit of the function when f goes to 0, you should say, oh, okay, the limit might exist, although the function is not defined. So this is where x is 0. If I look at the small neighborhood of 0, delta neighborhood of 0, at all of these points, the value of the function is 1. Constant 1. So the limit of the function is 1. So I can define f of x to be x over x when x is not equal to 0. When x is equal to 0, I can define the value of the function to be this 1. And then that singularity would be removed, which simply means f of x is equal to 1 always. That's what a removable singularity means, opposed to non-removable singularity. Okay. Okay, so we would say well, now it gives us another way of saying when a function is continuous. At a given point, say at a point, at some point, say a equals a1, a2. We say a function f with two variables, x and y, is continuous at that point if the value of the function at that point is equal to the limit of the function where x and y are going towards that point. What does that mean? Well, let me show you with one-dimensional case first. Look at this function. What is this function? This function f of x is equal to 1 when x is not equal to 0, but it's equal to 2 when x is equal to 0. Okay? Two questions. What is f of 0? Well, it is 2 by definition. What is the limit of f when x goes to 0? Okay, you should answer that. What is the limit of f? Not the value of f at 0, but the limit of f. The limit of f is 1. It means not to look at the 0 itself, but look at the points which are close to 0. And look at the value of the function at those points. Well, the value of the function at those points is 1. 1 is not equal to 2. Therefore, I would say the function is not continuous at 0. There is a jump at 0. So as you can see, this is an example of a function which is not continuous, okay? We have the same thing in higher dimensions. So let's look at some other functions. So are these functions continuous at the origin or not? So is f of x and y continuous at 0 and 0 or not? What is f of x and y? Well, let's say x minus y over x squared plus y squared. So is this function continuous at the origin or not? Well, first of all, there is no f of 0 and 0. I mean, what is f of 0 and 0? It's not defined really. How can I define f of 0 and 0? So let's try to define f of 0 and 0. Can I define f of 0 and 0? Is there any way to do that? I mean, it seems f of 0 and 0 is not defined. Can I define f of 0 and 0? Is it possible? Think about this for a few minutes, huh? Let's see if you can, just like x over x, is this problem here where we get at 0 and 0, we get 0 over 0? Is it similar to this thing? Or is it similar to 1 over x? So if you can define f of 0 and 0, it means it's removable. If you can't, it means it's non-removable. So think about it for a few minutes. So actually now we understand what it really means is that does the function f have limits when x and y go to 0 and 0? If it does, what is the limit? If it doesn't, prove there is no limit. The limit does not exist. Okay, so let's see if this function has limit or not. Actually, the answer is no. it doesn't have limits. This function f of x and y equals x minus y over x squared plus y squared does not have limits at the center 0 and 0. How can I see that? Well, look at the domain. What is the domain? Well, the domain is wherever this function is defined. It's defined where this guy in the denominator is non-zero. It is 0 when x is 0 and y is 0. So it's everywhere but the origin, right? Okay. If I want to show, if I guess a function does not have limit and I want to show that, I should try to go towards the center from different directions, right? Now this time, the directions I would try, one of them is this direction. And the other one is this direction. Well, along the red direction, we are on the line y equals x. So x and y are equal. So these points here are of the form xy, which actually it's the same as x because y and x are equal. And what does it mean to go towards the origin? It means x is going towards 0. What about the blue line? Well, the blue arrow is on the line y equals minus x. So here the points on this line are of the form of x and minus x, where x is going to 0. Okay. For the points on the red line, if I go, so what does it mean for a function to have a limit? It means if you go towards, for example, here, the center, the values of the function would converge to a fixed point. I want to say that's not possible. I want to say it matters on how you approach the center. If you approach the center on this red line, the values of the function would converge to something. If you approach the function on the blue line, the values of the function would converge to something else. Therefore, there is no fixed unique values. So here, f of x and y would be f of x and x, which is x minus x over x squared plus x squared. Because it's x minus y, but y is equal to x, so it would be x minus x. And x minus x is 0, 0 over anything is 0. So along this line, the value of the function is 0. Doesn't matter how close we are to the origin, everywhere on this function, the value is 0. What about the blue one? Well, on the blue one, f of x and y is f of x and minus x. Therefore, we have x minus y, but y is minus x, okay, over x squared plus y squared. So it's minus x squared. So in the domain, in the numerator, we have 2x. In the denominator, we have 2x squared. It would be 1 over x, okay? So on the blue line, we have 1 over x. If x goes to 0, 1 over x goes towards 1 over 0. But 1 over 0, when x is going to 0, 1 over 0, it's kind of converging to infinity. So on the red line, we have 0. On the blue line, we are going to infinity. They do not agree. Therefore, there is no limit. Okay, we can try to sketch the graph of this function to see how does it look like, right? So let's try to do that. Let's try to sketch the graph of this function. So okay, there is a question, but can we just say 1 is 1 over 0, 1 is 0, therefore no limit? Because no, we can say on the blue line, we have 1 over x, where when x is converging to 0, 1 over x is converging to infinity. It's basically the same thing as saying 1 over 0, but it's better. It's more rigorous. Yeah, you can just say 1 over x when x is going to 0 is diverging. It's going to infinity. And the other line, we have the constant limit 0. They do not agree. Okay, let's look at this, this function. It was x minus y over x squared plus y squared. Let's see how that looks like. Okay, as you can see, well, again, this doesn't seem to be very good at sketching these things, but as you can see, in some, if I come towards the center from this direction, which I'm showing with you with my mouse, it's kind of going to 0. Do you see? It's y equals to x. This line here goes to 0. If we go from this other direction, if we go to the origin from this other direction, from this direction, you can see if we are going towards the origin, we are going towards infinity. So maybe if I add the grid lines, we can see it better. Yeah, it's even a little better now. So if we go from this direction, we will go towards 0. If we go from this direction, we go towards 0. The interesting thing is that if we go on y equals minus x from the positive side, we go towards minus infinity. Do you see there is a hole there? It goes to minus infinity. If we go from the other direction, we go towards plus infinity. So there is no way that these things would agree. Adam has asked, how should we decide what lines to draw? It's just based on experience. Well, there are ways to find that out, but we usually don't talk about that in this course. And usually there are not many things in this course which you should try. They're just these 4 things I told you about. Usually those things work. There are some more advanced cases. I might solve some of them for you, but usually it's not very complicated. You can just guess. So here, for example, I looked and noticed in numerator we have x minus y, and I told myself if x and y are equal, x minus y would be 0, so the whole function would be 0. So that would give me one value 0. Can I get something but 0? Well, I have x minus y. If y is equal to minus x, x minus y would be 2x. So it gave me hope to get another value on the line y equals to minus x. So it's mostly based on experience, but there are some more general ways to find that. Okay. Okay, let's go back. Let's go and look at one more example. One more thing I should say. The same thing holds for 3-dimensional functions. The same thing as I said, but because we can't really see them, we can't see their graph, it's maybe a little harder to guess if they are, well, to understand what's going on. So for example, there is an example in the book. There's a function f from 3-dimensional space. We have 3 independent variables, x, y, z to r. It's 1 over x squared plus y squared minus z. Now the question is that, well, what's going on here? What is this function? Well, first, what is the domain of this function? Let's answer these questions one by one. What is the domain of this function? This function is defined wherever x squared plus y squared minus z is not equal to 0. So this function, well, the domain, first of all, note that because we have a function which defined on R3, the domain is a subset of R3. Okay, the domain is everywhere where x squared plus y squared minus z is not equal to 0. In other words, x squared plus y squared is not equal to z. Well, if we want to see when this thing is not equal to z, we should see first when they are equal to z. So what does this equation z equals x squared plus y squared describe? No, not saddle. Both of them are positive. Yeah, it's a kind of paraboloid. It looks like this. X, y, z. So the function is defined everywhere, but on this surface. So the function is defined everywhere outside of this surface and inside of this surface, but not on the surface. So the domain is the all of the R3 minus this paraboloid. Okay, that's our domain. Now, can we extend the function to this domain? Is there any way I can extend the function to this paraboloid, which I couldn't define? That's my question. So the whole part, the singularity now is not a point. Singularity is equal to a paraboloid, which is a more kind of complicated form of singularity. Singularity is a whole surface now, not just one point. And my question is that, is it removable or non-removable singularity? Can I extend the function to this singularity? Let's try one of them. For example, 0, 0, and 0 is one point on this paraboloid, right? It's one of the points which I can't, which they are not in domain. It's one of them. Can I extend the function to this point? Let's try to get close to this point from different directions. Try to do that. Let's see if we get different things. Think about this one for a few minutes. Can you extend the function to this paraboloid? More especially, can you just extend it to one of these points? Just say 0, 0, and 0 or not? Think about that for a minute. Okay, someone claims it's non-removable. Can you tell me what are the lines or curves you chose to show it's non-removable? Approaching z from above. Okay, so the one thing we can do is approach this point from above. That's one direction. What about the other one? The other one, you should give me two of them. That's one. Approaching y from right. Okay, and then the other one might be like this. Let's try these two. So, yep, we can also approach from here. Let's try some of them. So f of x, y, and z is 1 over x squared plus y squared minus z. The domain is all R3 minus this parabola. We want to see, so the whole parabola is a singularity. So we want to see if this singularity is removable or non-removable. So an easier thing to see if it's removable only at one point. If we can't even remove one point of this surface, of course, we can't do that with all the surface. And it means if this function has limits at that point or not. When x, y, and z, they go towards 0, 0, 0. So one idea to show the limit does not exist is to go, so non-removable means the limit does not exist. So it seems we want to show, we're trying to show the limit does not exist. So we should go towards this point 0, 0, 0 from different directions. One direction is the points on this axis. Well, the points on this axis, the first two variables are 0, the last one is z, and z is going towards 0. Okay. What is the value of the function at 0, 0, and z? Well, it's simply 0 plus 0 minus 1 over z. And when z goes to 0, it goes to infinity. But that's the point. Actually, we don't even need to take two different directions. Is it plus infinity or minus infinity? Well, it depends. If we go from above, z is positive, right? So minus z here we have would be negative. 1 over a negative number is another negative number. So when z is going to 0, although this thing is going towards 0, but so it means it's very, very, very small. But minus that very, very, very small number is a negative very, very, very small number. So here we have a very, very, very small negative number in denominator. 1 over that goes towards infinity, but because we have positive over negative, it's negative infinity. So on this red line, we go towards negative infinity. Now if we converge from below to same point, here z is negative on this blue arrow, right? We get the same function, we get 1 over minus z, but z is negative. So minus z is positive. 1 is also positive, so 1 over minus z, the whole thing is positive. Now, if z goes to 0 from this blue arrow, although it's going to 0, and it would be very small, but it would be a very small negative number, minus z would be a very small positive number. And although 1 over 0 goes to infinity, because it's positive, it goes towards plus infinity. So on the red arrow, we go to minus infinity. On the positive arrow, we go towards plus infinity. So on different directions, we go to different things. It's not like that it goes to infinity. Also, the sign matters. It's like 1 over x. One of them goes to plus infinity, the other one goes to minus infinity. So there is no limit, therefore it's non-removable singularity. Unfortunately, unlike the previous ones, I cannot sketch the graph of this one for you because the graph of this thing, this is the domain, right? This is like the map. The graph would be something 4-dimensional, which we can't sketch. Okay, so this was part section 13.2. We finished section 13.2. So 13.1 was about domain. Section 13.2 was about limits and continuity. So with considering today, we have 10 days, I guess, if I'm right. Am I right? Can anyone confirm me? I guess we have 10 more meetings. Anyway, if I'm right, we have 10 more meetings. Every day, we break every day into 3 smaller meetings, into 3 classes. Am I wrong? No, I mean, well, each day. Well, I mean, each day we have 3 classes. Let me look carefully. I mean, each day I'm considering 3 classes, 3 or 2. Let's see. Yeah, I guess I'm right. Yeah. So we had limits and continuity. Now, the next thing we should discuss is 13.3. It's about partial derivatives. Okay, so we are on track. The third topic we talked today is partial derivatives. So we had a 10-minute break. Maybe we can have a little longer break. We can have, we can continue at say 11, say 55. We can start with partial derivatives at 11:55. It would be half of the chapter 13. Is there any question up to this point? Okay, so let's have a short break and we would come back.